About models, language, and semantics. And we are going to have 3 papers are going to be presented. And we start with the paper from Federal University of Rio de Janeiro. It's going to be presented by João Souza. So João, you can start your presentation.
Okay, you can see the slides, right?
Yes.
So good morning, everyone. My name is João Batista. I'm from the Federal University of Rio Grande do Norte. And today I'm going to present a work that proposes a model for large-scale data processing programs. These are the topics that will be covered in my presentation. I will start by introducing the contributions, the context and motivation of our work. Then I will introduce the 2 formalisms that use. After that, I present the model that we are proposing, and I present a first case study where we apply the model. I finish with conclusions and future work. So to start, in this work, we are proposing a model for large-scale data processing programs in data flow-based systems. Our goal is to allow the specification of data processing programs independently of the systems. In this manner, the program can be specified before the system is chosen. Also, having an independent specification allows the same program to be implemented in different systems. Our model is organized into 2 levels. In the first one, the data flow program is represented as a directed acyclic graph or DAG. And in the second, the transformations represent operations on distributed data sets. We formalize the data flow with Petri Nets and the transformations with Monoid Algebra. As a first case study, we apply our model in the context of mutation testing. So the growth in data production in recent years has introduced a series of challenges for its storage and processing, since traditional approaches were not prepared for this amount of data, a phenomenon that is called big data. So to deal with the challenges of big data, different technologies and programming models have been proposed. Examples of that are the system Apache Hadoop, that adopts the control flow model, and the systems Apache Spark, Apache Flink, Apache Beam, and DryLink that adopts a data flow model. This later, the data flow-based systems have gained a lot of popularity in recent years. And this is because the systems hide from the user details and complexities that are inherent to the distributed and parallel environment. Allowing developers to deal only with the logic of the program. In addition, these data flow-based systems share several features. In the first one, a program is defined as a sequence of operations on distributed data sets, which in turn represent a DAG with the program's execution plan. Also, they provide abstractions for distributed data sets. And finally, they all offer a comprehensive set of distributed operations that includes operations for mapping, filtering, and aggregation, besides other types. So in the figure below, we have a representation of a distributed data set. We can see that the different data blocks are partitioned in different nodes in a cluster. But for the developer, it deals if they were only a single distributed data set because of the abstractions these systems provides. And with that, developers don't need to worry about the parallel and distributed computing. So to exemplify, let's consider the following data flow program in the system Apache Spark. In the simple program, we want to get the unique log messages into 2 data sets with log files. So this program receives as input these 2 data sets. And first, we apply an operation to merge these 2 data sets. After that, we apply an operation to remove duplicate data. And then we apply an operation to remove header messages. We finish returning the resulting data set. Internally, this program is represented by a DAG. So the DAG that is generated by Spark is represented in the figure below. And since the other data flow system offer a similar data flow model and also similar operations, we can use the same logic that we use to this program for the other systems. But even with these similarities in the programming model, each system deals with the parallel and distributed processing, data treatment, and optimizations in different ways. So this leads to with this, the systems can have different performances according to the context or available resources. So the choice of the systems can be made based on different factors, such as non-functional requirements, the available infrastructure, and even preference of the development team. But since I mentioned that the systems provide a similar programming model and a similar group of operations, it's possible to specify a program independent of the system. So to address this, in this work, we are proposing a model for data flow programs that is independent of the system. So now I present the two formalisms that we use in this work. The first one is Petri Nets. That is a formalism for modeling and analyzing distributed and concurrent systems. So a Petri net is defined as a graph with two types of nodes. The first is the places that represent the state of the system, and transitions that represent the actions that can change the state of the system. Also, we have directed edges that connect places and transitions. So in the figure below, we have the representation of a simple Petri net, where we can see 4 places that are represented as circles and 2 transitions that are represented as bars. Also, we can see that in the first 2 data sets, we have tokens that are used to represent the current state of the systems, that in this case is ready to execute. The second formalism we use in this work is the Monoid Algebra, an algebra for data-centric distributed operations. This algebra uses monoid collections to represent distributed data sets that can be bags, which are unordered data collections, and lists that are ordered data collections. And also monoid algebra offer basic distributed processing operations that are defined as monoid homomorphisms. These basic operations include operations for mapping, grouping and aggregating data, and also to order data. So below we can see a simple example of some operations of the monoid algebra. In the first one, we are mapping the data in a bag by applying a mapping function pass as parameter. In the second, we are grouping key value data. And in the third, we are aggregating the data in a bag. So now I introduce our model for data flow programs. The model is divided into 2 parts. The first is the data flow, and the second are the data sets and transformation. So in the first part, the data flow models a DAG that defines the program's execution plan. So in our model, a program is defined as a Petri net that contains 2 types of nodes. The nodes of distributed data sets that in the Petri net are the places and belongs to the set T. We also have nodes for transformations that represent distributed operations, and in the Petri nets are the transitions. We also have the set of edges E that connects data sets and transformations. So these three sets represent a program in our model. So to exemplify, let's consider the same problem where we get the unique messages into two data sets of log files. So in this program, we can identify 5 data sets that are 2 input data sets and other 3 that are generated with the application of operations. And also we can identify 3 transformations. So translating this to our model, we obtain the following data flow with a set of data sets D containing 5 nodes and a set of transformations T with 3 nodes. And in the part below, we have a graphical representation of the data flow of this program. The second part of our model defines the semantics of the data sets in D and transformations in T. And we define these semantics with monoid algebra. A distributed data set in D can be are represented by monoid collections, which can be bags or lists depending on the order of the elements are important or not. And these monoid collections capture the concept of the abstractions for distributed data sets that are provided by the data flow systems we analyze, that are the RDD in Apache Spark, PC collection in Apache Beam, dataset in Apache Flink, and dry table in DryLink. The transformations define operations on data sets and are defined in terms of the operations of monoid algebra. Transformations can receive 1 or 2 datasets as input and produce 1 dataset as output, and also can receive functions and literal as input. The set of transformations we defined in our model was based on the main operations defined in the analyzed systems. So these transformations are grouped according to the type of processing that is done, which are mapping, filter, grouping, set-like operations, aggregation, join, and sorting. So here we can see the definition of some transformations. In the first, we have the map transformation that transforms data in a data set by applying a mapping function. In the second, the filter transformations, it removes data based on the predicate function that is passed as parameter. In the reduce by key transformation, we aggregate data that is grouped by key. And in the last one, the union, we merge 2 data sets. These are just some of the transformations defined in our paper, but we can see the definition of more transformations in the paper, since we define for other types of data processing. Now I introduce the case study where we apply our model. We apply it in the context of mutation testing, which is a fault-based testing technique that simulates faults to design and evaluate test sets. Faults are simulated with the application of mutation operators, which are rules with modification patterns. So the application of a mutation operator in a program generates mutants that are versions of the original program with some modification. So in a previous work, we proposed a set of mutation operators for data flow programs in the system Apache Spark. These mutation operators also are divided into 2 groups that are mutation operators for the data flow and mutation operators for the transformations. And we used the model proposed in this paper to formalize these mutation operators. So the first group, the mutation operators for data flow, the model changes to the DAG that defines the program. So to exemplify our mutation operators, let's consider the program represented in figure A. Here, for simplicity, I changed the color of the transformation to simplify the identification of each transformation. So these operators of this group make change to this DAG. So our first operator replaces one transformation with another that is in the deck. So in the case of figure B, we replace the transformation in orange with the transformation in green. Our second operator changed the execution order of two transformations. So this is represented in figure C, where we change the order of the transformations in green and in orange. In our third operator, removes the calling of a transformation in the program. That is represented in figure D, where we remove the transformation in orange. Our second group of mutation operators model change to specific transformations. So in general, we model two types of modifications. In the first, we make change to the function that is passed as parameter for the transformation. And in the second type of modification, we replace a transformation by another of the same group. So to exemplify mutation operator for transformation, let's consider the transformation that replaces a set transformation. So let's consider that in our original program, we are applying the transformation subtract with two inputs data sets. So applying this mutation operator in this program, we obtain the following five mutants. In the first, we replace subtract with union. In the second, replace with the intersection. In the third and the fourth, we replace the original transformation with the identity of the two input data sets. And in our last mutant, we change the order of the two input data sets. To support our approach, we developed the tool Transmute Spark that automates the mutation testing process in Spark programs. In this tool, we use the model as an intermediary representation. And by doing this, we plan to extend the tool in the future to apply it in programs in other data flow-based systems. So in this picture, you can see an overview of the workflow of our tool. And we can see in the beginning that the tools receive as input the source of the program and translate it to implementation of our model, and then continue with the process of mutation testing. So to finalize presentation, in this work, we present a model that can be used to specify big data processing programs in data flow-based systems. Our model was created to represent the main features and operations that can be found in this type of system and can be used to specify a program independent of the system. So we can specify the program first and decide later which system we use. As well, we can specify a program and implement it in different systems. And as a first case study, we applied the model in the context of mutation testing, where we used the model to formalize mutation operators and also as an intermediary representation in our testing tool. As future work, we plan to extend our model to use colored Petri Nets. And with that, we want to use the CPN tools for analysis and simulation, since this is a part that we didn't explore in our work yet. As I mentioned, we also plan to extend our testing tool to apply the mutation testing in programs in other data flow-based systems. And lastly, we want to use the model for code generation in data flow systems. So thank you everyone for your attention.
So thank you, João, for the very nice talk. It's a very interesting work. So if you have questions, you can just type on the chat. For the moment, we don't have questions, but I have two questions, and I will ask them. And then if anybody wants to ask question, please Just type and I will read it. So my first question is, why are you using direct acyclic graphs? Why not having cycles? And why, even if you are focusing on acyclic graphs, why do you emphasize they are bipartite, since this is like a direct property that they have? So my main question is, why not cycles? And is this a limitation?
In this case, this is a characteristic of these data flow-based systems. Some of them allow the implementation of iterative programs. So some of them allow cycles, but in most of them, they don't allow this, don't allow cycles. And in most of the case, they are represented only as a DAG. So this is why I represent it only as a DAG. But I consider to extend the model in the future to add this feature to allow the specification of programs that have cycles. That is mainly using programs that are used for machine learning. So I plan to do this in the future, but since the majority of the systems that we use don't allow this, I didn't put in the model yet. And in the case, I represent it as a bipartite graph because of the two types of the two main abstractions that we identify in the systems, that were the distributed data sets and the transformations, the operations. So I represent this in creating these two types of nodes representing our model.
Okay, thank you. So we have a question here from the audience. Gustavo Carvalho is asking, what do you plan to gain from use CPNs instead of PNs?
In this case, we didn't analyze yet the which system for Petri Nets we should use, because we didn't explore yet this part of simulation. In the case, I refer to the CPN tools because it's already well known and well used. But this is a part that we still plan to analyze more the options and see how we use, how we address this part of simulation. And then we reanalyze the systems that we use for that. But the CPN tools was a first idea. I didn't analyze the other options.
Okay, so I have a last question. You have so far, at least from the paper, you have experimented your model on the testing field, which I think it's very promising. I like a lot what you showed about the mutation of the operators. So I think it's an adequate approach for this testing purpose. What about the usual modeling development setting? Have you tried your model for supporting development at all? Like even if in small toys? Or this is really target at testing?
No, this is one of our plans to future work, since we want to explore the part of generation of code. So we didn't do this yet. For now, we applied only in the context of testing. But yes, it's a possibility to use it to specify uh, a program and implement it. Is actually is the main one of the main ideas of our model. But we plan to explore this part in the future also.
And perhaps this is like internal tool as well, right?
Yes.
Okay. If you have any other questions for the authors, the work is very interesting. I think it has a large field of application and interesting questions to be answered and discussed. So please go to the Slack channel and talk to the authors. And thank you again for João for the very nice talk. And we should now move on to the second talk.
Okay, thank you.
Thank you, João. So the second paper is reversal fuzzy switch graphs. Is going to be presented by Rejvan Santiago, also from Federal University of Rio Grande do Norte. And so, Rejvan, you have about 4 minutes to set up your presentation. So do not hurry, we have time.
Can you hear me, Patricia?
Yes.
Yes, are you seeing my screen?
Yes.
Okay, I'm ready to begin when you want.
Okay, so let's just wait like 2 minutes so that if anyone get late, will not miss your talk. So, Rejvan, if you think you are ready, you can start.
Okay, thank you very much. Good morning for all. This is a work that is making with Sony Campos, da Universidade Federal do Rio Grande do Norte, Manuel Martins e Daniel Figueiredo from Universidade de Aveiro in Portugal. So this is a new structure that you are proposing in this symposium. This is a new structure to model and to verify some kind of systems, which is called reversal fuzzy switch graphs. It is based on a previous work that we have published in soft computing called fuzzy switch graphs. And now we will provide the context and in which this structure was conceived. So the story starts with a work of Dov Gabay and Sérgio Marcelino, with the idea of switch graphs. They intended to model reactive systems, and the difference of this kind of graphs to usual graphs is that this kind of graph has higher order arrows that start with, from first order arrow to other arrows of different levels. So this kind of structure can model a standard situation like this. The penguins are birds that do not fly. Tweety is a special penguin that does not fly. If we want to model this first statement here, we can start at the node. Wow, it's not okay. Wow, I have problems here. I have problems here. I need a timer. Patricia, is it possible? It's very fast. I can solve this problem. Okay? Are you hear me? Hola.
That's okay. That's
okay.
okay.
It's very fast. I have compiled with a run compiler. Oh my God. Ser compilado com X-Stack. Okay, that's okay. So it's okay now. So excuse me, I compiled with the wrong compiler. So as I was talking, so the idea of sweet graphs is that they will model system with contains reactivity. So, for example, you have these two standard statements. Penguins are bees that do not fly. Tweet is a special penguin that does fly. We could model this situation by walking on this graph, starting from penguin, the knowledge penguin. We have a penguin, so you know that it's a bird. And when you go to the knowledge that it's a bird, you activate this arrow that will deactivate the access to this knowledge does fly. So you disconnect this arrow here, and you cannot access that the penguin is a bird that flies. The same here. Now, if you use the same structure to model the situation, you have to start from the son of tweet, which is a special kind of penguin, which is a penguin. And now you activate this high order arrow here that you deactivate this arrow, which will also deactivate this first order arrow here. So now you can access the knowledge of das fly. So that's the idea of sweet graphs, which is which model this kind of things. So based on these ideas, we proposed the idea of a fuzzy switch graph. A fuzzy switch graph is also a graph that has higher order arrows. However, in this model, we don't have the device to deactivate or activate arrows. The idea here is that you have a graph with high order arrows, with fuzzy values on the arrows, but also with an aggregation function. An aggregation function is a function that works like means, like geometric means, like arithmetical means, and that it's available in all the graph. Let's see how does it works. For example, consider that your global aggregation is the arithmetical mean, and you want to go from X to Y. So the graph will work like this. You start in X and go to Y, and you use these three values here. Look that you have a high order arrow that is arriving in this first order error whose value is 0.1. So you want to use these three values and aggregate. And the aggregation here is the arithmetical mean that you use to update the value of this arrow here. So how does it work? You have a thing like this. You have updated the value based on the three previous values and where you applied the arithmetical mean. So uh, now you can extend this value, fuzzy switch graphs, to fuzzy reactive graphs. Now, the unique difference is that you have you can have different aggregations for the same graph. You assign to each first order arrow an aggregation, which is given by this function here. So for example, to the first order arrow xu, you can aggregate the arithmetical mean. And to the arrow uy, you have associate this different aggregation keys the maximum. So for example, if I start from x and go to y, I will aggregate these three values to update the value 0.4. Since it's the arithmetical mean, I have 0.3. And now when I go to u to y, I need to update these two arrows here, vy and this arrow here, excuse me, this arrow here, which has the value 0.2, which is also a high order arrow. So when I cross the path, I update the value. So this is the idea of a fuzzy reactive graphs. Okay. Now, we want to introduce the device to activate or deactivate fuzzy switch graphs and fuzzy reactive graphs. So to achieve that, we have to introduce a label which states that a arrow is activated or deactivated. So this is the difference. This is the same way that we built the previous model, but we add a label which states that, which marks if the arrow is updated or deactivated. And so the arrows here, the high order arrows now are can activate or deactivate or activate the target arrows. Arrows that not activated is denoted by this kind of line here. So arrows that has the role to activate denoted by few arrowhead, and arrows with the activate arrows are not filled. So let's see an example. Consider that you have here, we also in reversal for city graphs, the aggregation is also global. All the arrows will use the same aggregation. So see, for example, the arithmetical mean as the global aggregation here. And you want to cross the path x to u and u to I, and you have this situation here, x to u, and we want to update this value here, and we want to deactivate the arrow from x to I. So we get this situation here. The same, if you want to go to u to I, we want to update these values, deactivate this arrow from y to v, and deactivate it does not have any effect here. Deactivate this arrow here, so we get this situation here. In the paper, we have proved some properties on this new structure. We show, for example, that if the aggregation, the impacts of the aggregations in the resulting graph. For example, if your aggregation is conjunctive, which means that all the values are below the minimum function, and when you cross the path and you apply the aggregation, you get a subgraph of the previous graph. If the aggregation is a disjunctive, which an aggregation that is greater than the maximum, you get a supergraph. We have also proved other properties, like if your aggregation is shift invariant, then the resulting graph is as a translation of the previous graph, and you have also some properties that we have proved that is written in the paper. So now we come to the idea of reversal fuzzy or reactive graphs. That's the same idea as we did before. We have just to enable the graph to have different aggregations for different edges, which we can do it by introducing this function here, which assigns each first order arrow to a set of aggregations. So that's the same idea, but now we have different aggregation. For example, from X to I, we use the arithmetical mean, and from U to I, we use the maximum aggregation. That's the same idea, so that the aggregation is not more global. Introduced, provided the product of reversal for switch graphs. As you can see, you have copies of these two graphs in the resulting graph. The components are copied, are put together in the product of reactive graphs. We provided the same for reactive graphs. Now we have just to take into account how is the function that assigns each aggregation to each first order arrows. We achieve that by marking the aggregations and in defining the aggregation from this set, from the set to the set of this disjunct union, and you apply the respective aggregation from the respective graph. Now that you have this new structure, we provide a logic for that. It's a model logic. It's a simple model logic where you have a propositional language with two modalities. The first modality means that phi is true in some next state and phi is true in all next states. We have just to take care here, because to access another state, we have to guarantee that the path is on. So we have to take into account these two kinds of sets. That is the set of first order arrows, which connect words, and which are on. And this is the set of words that are connected with W by active arrows. So the semantics for this logic is usual, but taking into account just that the connection must be active. It must be the arrow must be on. So let's see how we can use this structure and logic in a concrete situation which controls the level of a fluid in tanks. Suppose that you have this situation here. You have a tank, and you have to control the level of fluid here. We have three sensors here, which reads the level of the fluid, and you have pumps here to control the level, to dry the tank. So you have two pumps, three sensors, and a fluid electrical discharge. We can model it by assuming that they are words, states, and we have a reactive fuzzy switch graph to model this situation here. Let's see how it starts. Suppose that we want that when the fluid level increase, we want that the electric current that is assigned to each cable here increases too. when the level decreases, we want that the electric current that is assigned to the electric cable here decrease. How do we achieve that? We assign to each path here, for example, from ST1 to ST2 that is increasing, we assign the maximum. And when we decrease, you assign the minimum. So let's see how does it works. So if you start here and you arrive in the first sensor, and then we move to the second sensor, we will activate this arrow here. You have to activate the pump because you want to decrease the level of fluids, and to achieve that, you have to increase this current here, and you do that by applying the maximum aggregation. So it becomes on, and you activate the pump here. Now suppose that again you continue to increase. The pump is not enough to decrease the fluid level, the level of fluids, and then you have to assign the second pump, and you do the same. Now the things are working, the fluid becomes to decreasing, and you have to decrease the value of, you have to turn off this pump. And so you have to apply to decrease the current value here to become to the previous value. So you apply the minimum, and it becomes 0.5 again. 0.5 again. Again, you decrease the value and deactivate the pump and go to the start case, to the start states. Now, how do you apply the logic here? Suppose you have this model here, and you have two proposition. The pump 1 is active, the pump 2 is active, and you have the proposition pump 1 is active at sensor 1, the value is 0.05. In ST2, 0.08, is SP8, 0 in sensor 3, 0.6, and so on. Now you want to verify the following proposition at the sensor 2, at the second sensor. There are some next states in which both pumps are on. So how do we verify the fuzzy grade of this proposition here? We apply our calculus, applying the Gödel semantics. We can change the semantics depending on the semantics we want. We use the Gödel semantics. So applying the Gödel semantics, you obtain that the value of this proposition is 0.6. So meaning that the degree of the sentence, there is a next state in which the pumps P1 and P2 are working, at state ST2 is 0.6. So, as final remark, we are in the beginning of this work. This is a first, how can I say, the first vehicle that we are publishing our work. We have some ideas, for example, to how is the B simulation in this kind of systems, the definition of homomorphisms, verify some other applications. How is this work, for example, to verify other kind of reactive systems? And so that's all. Thank you very much.
Thank you, Regivan, for the nice talk. So if you have questions, you can just type on the chat. I have a few questions while. Okay, there is one here from Rodrigo. And the question is, can fuzz switch graphs and by extension reversal fuzz switch graphs be applied to undirected graphs, or do they require a directional approach in order to work?
The idea, we have not yet verified this, but I think that it's not how can I say, intuitive. I cannot interpret how could you interpret a fuzzy sweet graph when you go in two directions at the same time. For me, it's because the idea is that if you cross the path from one point to another, you activate an aggregation. If you go to another, for example, from A to B, you activate an aggregation and activate or deactivate another arrow. And if you go from B to A, you can activate another aggregation. I have not verified this point of view. I don't know if it makes sense.
Okay. Okay. So another question. I will ask a question while maybe there are some other questions here. Do you have some kind of target systems in mind? It seems like the approach is, well, the model is suitable for control systems in general. Is this your target?
No, it's not my target. Actually, I am working with the fuzzy community, and in fuzzy community, you have many applications. It's true, you have many applications in control systems. And for me, it seems natural that this model could be applied to control systems. However, as I said in the end of of my talk, we are verifying how could be other fields of application. How could, for example, how could you apply the systems to reactive systems in computer science, for example? We have to take into account that although you are working with fuzzy values, fuzzy logic contains fuzzy logic in some sense. For example, it's possible to use this model where the arrows contains just values 0 and 1. And you could, for example, obtain reactivity in usual computational system. But we have to see how does it work. How could, for example, how could works a calculus of that involve reactive systems? How could you represent in this system? As I told, we are in the beginning of the work. There are a lot of things to do in this field.
Okay, thank you. When I read your paper, I was thinking about also autonomous systems and things like that. But that's something you are going to consider in the future, I believe. I missed one question here from Gustavo. Gustavo asks, do you plan to provide tool support for this data structure and the corresponding logic? If so, what would be the main challenge?
What does he mean by support? I don't understand. A language to provide a formal language to write.
Gustavo, can you, a software, he means like perhaps a software for supporting the modeling and reasoning?
It's a target, but we have to find candidates, students to do that. That's we aim to provide a software for that. I think that this model with the idea of activation, the activation of a resource, we could see this model as the states as a resource of a systems. Now we are writing a paper that we have operations of such a graphs where you extend, for example, you have a system and you can extend the systems with other functionality. For example, you have alarms and other sensors, extra sensors, and so on. And we have operations to deal with that. And I think that's it's important to have a software there. But now I don't have any idea about it. I have to. We have wrote this paper in the, how can I say? I think that's 2 or 3 weeks ago, and it's in the beginning.
Okay. Anyone? Any more questions? Okay, so thank you, Hajma, for the nice talk and the discussion, answering the
Thank you
questions.
very much. It's a pleasure to see you and to see some colleagues here that I don't see for a long time. It's a pleasure to see you all.
Okay, so thank you. And if you have more questions, please go to the Slack channel for the session. And so let's now move on to the last talk. So we have some time for the setup. So please feel free to start. João Paixão is going to present the paper Calculation of Proofs in Relational Graphical Linear Algebra. So João, you can.
Thank you. Can you hear me? Yeah.
Yes. So if you think you are ready, you can start.
Let me just put in my. Can you see my screen?
Yes.
Perfect. Should we wait a couple minutes? Or?
I think you can start now. So if you have any problems, we have time to fix. So
Okay.
you can just start.
Perfect. Good morning, everybody. Thank you for being here. Thanks for the organizers. I'm going to be presenting calculational proofs in relational graphical linear algebra. This is joint work with Pablo Sobocinski from Tallinn University of Technology. And I'm from Universidade Federal do Rio de Janeiro. One of my main personal motivations is that I've been teaching linear algebra at UFRJ for the last couple of years. And there has been an increase on the number of students from areas outside of math, computer science, and engineering. They're really interested in linear algebra. They need to learn linear algebra for various things they're doing at the university. And I found they have a lot of difficulty with proofs and proving things in these classes. They have difficulty with a large number of concepts there is in linear algebra. They have tough time understanding all the concepts, the dualities, the many names that we have in linear algebra. So a couple of years ago, I went to search for new material to help them. And I stumbled upon graphical linear algebra, which is a very visual language for linear algebra, which is both diagrammatic and it's a formal language where you can actually prove things and reason, right? So this graphical linear algebra was developed by two different groups independently, and today what I wanted to show you is that our main contribution is a small set of axioms for linear algebra, which highlight the dualities and symmetries of linear algebra in this context of graphical linear algebra. Let me just jump right in to the diagrams. So the whole language is with diagrams that are representing processes. And let me make this smaller here. And then we have inputs and outputs, and in each of and you have these processes going from left to right. Okay. And the first, this is kind of making a breakfast here. But in linear algebra, the first diagram that's important for us is the sum diagram, where it has two inputs and one output. And I'm going to represent by this white node here. So numbers are going to come in, processed by the sum, and the output output the sum. Okay. So that's how we're going to denote sum in graphical linear algebra. Another pieces that we need to build this language, this graphical linear algebra language, is we have the identity process, which just takes anything in and outputs the same thing. And we're gonna denote by this one-to-one diagram here, is just a straight line. And also the twist. where I can exchange the input and output, the order of them, and then we can use this this piece right here. But how do you build, create other diagrams, more complex diagrams in this language? Okay, the first thing you can do with these pieces, these small pieces, is you can combine them in series. All right, and then you can compose them in series, and you make bigger diagrams. Okay, so serial composition is one of our operations. The other operation is parallel composition, where you can stack things on top of each other. For example, the identity parallel with the sum, you get some diagram like this. When you sum and you parallel with the identity, you get another diagram like this. So series and parallel composition are the only two operations we're going to use to build our diagrams. So for example, the breakfast example could be done by doing parallel to the identity, parallel another identity, get a crack egg, and then you can combine these, and then you can compose them sequentially, right? So any diagram has to be built this way in our language, okay? If you can do that with the pieces I told you, then you have a diagram that we're talking about here. Then after, to develop graphical linear algebra, you need to come up with some equality rules, okay? Some equations in our theory. And one of the first equations that we have is that you can untangle wires, all right? The wires never get tangled up. So you can move them around and you can untangle them. So you have this swap. With the swap gives you two identities here. And you can move things around in more complex scenarios as well. Another thing you can do, the generators, each one of the little pieces can kind of move around, right? You can move them back and forth. Oh, sorry. You can move them back and forth, and it's very topological language, right? Everything you can move around. So you can move it up and down. It's no problem at all, right? So these are some of the rules. Now we start getting to the common rules that we're used to in basic math. For example, the sum is commutative, so it doesn't really matter the order of the inputs. So we have this equation here to represent that the sum is commutative. Okay, so this x plus y, this is just the semantics. What you're supposed to be thinking about, it's happening, but the graphical language just has the graph with the y node in it. Okay, so x and y and x plus y are just the semantics. So also sum is associative. You can group addition any way you want. So you have this graphical equation here that you can use. Okay, and this represents associativity. Another thing that we have is also we wanted to represent unity. So we have this new generator which just outputs 0. Okay, anything that this white dot here with just one output here, it's just outputting 0. And if you sum up with 0, you get back the identity. Okay, this is kind of like 0 plus x equals just x. Okay, so far so good. This is what we have as the equations for our theory. Okay, and for example, after you have these axioms, you can start proving theorems in this graphical language. Okay, you can do a proof graphically, right? And for example, you have this theorem here that we don't have it yet, right? This one, the 0 is on top. This one, the 0 is on bottom. I also want to prove that this is the identity. Okay, one of the things I can do is start a proof. I do commutative law, and then I slide my 0 all the way up here, and then I can finally use the identity. Okay, I hopefully you're not getting all the steps, but just trying to get you the idea of what's a graphical proof will look like here. So you're using commutative, you're using the sliding rule that you can move things up, and then we finally use the unity. So these are just justifications. So you have this theorem here. Now this is not an axiom, this is something that we derive. One of these interesting things about graphical linear algebra is the duality, and the duality really, the duality really shows up let me, oh, the duality really shows up when you add another generator, the copy generator. This is something that we usually don't see in school. There's no famous math symbol for the copy, but the copy machine is just an input that make 2 copies of them, okay? And that's we're gonna represent by the black dot. And also, together with the copy, there's a discard machine. So anything that comes in here gets discarded. It has no output, okay? So it's a machine with just a 1 input and no outputs, and it discards. We can call this garbage. It's a garbage can. Okay. And the interesting thing is the laws, the axioms for copying are exactly, they're very closely similar to some. Okay, so copy is also commutative in the output, right? If you make a copy, it doesn't matter which side is first, which side is second, what it comes out. You can group copies in different ways. Copy is also associative. And copy with the discard, okay? When you copy and then you discard is the same thing as doing nothing, doing the identity, okay? So copying has also the 3 properties that some have, but relating the output, okay? So you already see a nice duality here between copying and adding our 2 main operations, our graphical linear algebra. Every equation here, if you flip it and you change colors, you get something on this side. So this is the duality: flipping and switching colors, you get everything the same. Okay, and this is a really nice property for graphical linear algebra, because if you have a theorem here that you want to prove, for example, this one here with the black colors, you can also, we already proved one theorem that's very similar, that's dual to it, that's flipped and switched colors. If we already have the proof of that, all we have to do is just change the axiom from the sum axioms to the copy axioms, and we're gonna have the same. We're gonna have a proof for that equation. So you buy one, you get one for free. You prove a theorem, you get another one for free, because the axioms have this nice symmetry between them. So the proof will be exactly the same, but using the other side of this table, okay? So this is the property we get. Graphical linear algebra is nice too, that you can, diagrams, we can write the process of multiplication by a natural number by a 1-to-1 diagram. For example, here, if you make a copy of the x, and then you make a copy of x again, and then you sum, and then you sum again, that's the same thing as multiplying x by 3. Okay, so we're gonna call this whole process here 3, multiplication by 3. And this is the 2, and this is the 1, and there it goes. Okay, so the process of multiplication by a natural number is derived in our language. We can write as a one input, one output diagram. And it's pretty nice that after you've done the natural numbers, you can start doing matrices of natural numbers. For example, this 2x2 matrix that gets a x1 and x2 and computes x1 plus 2x2, 3x1 plus 4x2. Just a matrix that we learned in the first week of linear algebra. We can write this graphically, all right? Having two inputs and 2 outputs, and then you do the natural numbers that you already built up. And this right here symbolizes this matrix, okay? And you can do this for all the matrices and n by n matrices. They're gonna be n by m diagrams. This is just an example of the 2x2 case, okay? So you can do matrices in this language just using the copy and the sum operator and the techniques I showed you. Okay, so but the only problem is that this gets really, really ugly if you start drawing bigger and bigger diagrams. Okay, imagine this being a 5x5 matrices. Then you're gonna have wires going all over the place. But the nice thing is now that then we need to abstract. We need to start introducing syntax to just to make the diagrams cleaner. For example, if you have a bunch of identities all stacked on top of each other, that's very common to do. We're gonna just write down as identity with this K number here, so you don't have to draw all the identities. Also, the same thing. If you have 3 different things that you want to make a copy and they're all coming in here, one thing you can do is we can generalize the copy operator, so it will make copies here of the 3 things and make copies here of the 3 things. So imagine an x1, x2, and x3. Then you're gonna get x1, x2, x3, x1, x2, and x3 on the output. So generalize the copy machine to be able to take a bunch of numbers coming in. So you can imagine this being a vector, with three components, and it's making a copy of this vector here and here. Okay, so this is the generalized copy. We can also generalize the sum. This is essentially to sum vectors. You have just m numbers here, and then you can sum them up and outputs here. And you also have the generalized 0 and the generalized discard. So once you do this, you can start drawing bigger diagrams without having to worry that the drawing is going to be weird. So one of the things is, one of our first main contributions is what other axioms do you need to be able to deal with the algebra of matrices, for example, right? And we were able to draw up a couple axioms in this generalized language, where, for example, we asked the question: how are the diagrams? How do they interact with these generators? For example, like we want these diagrams here to be able to represent matrices. So we knew that 0 applied to a matrix has to be 0. Okay, this is a simple property of linear algebra. So we drew this up. And then you have, for example, if you have 2 vectors here and you add them, and then it passes through a matrix, right? So for example, pretend this is x1, this is x2. You add them and then you multiply by matrices. Then we want to know that we know that matrices are linear. So you're able to first multiply by the matrix and then add them. So this axiom here, is essentially trying to encode the linearity of linear algebra in a graphical way. Okay, so you have you can sum first and then multiply, or you can multiply by the diagram and then sum. So this encapsulates linearity, and we were able to establish these axioms, and we did the dual version for the copy, and we verified that they look good as well. If you multiply something and then discard, it's the same thing as just discarding. Or if you multiply something by a matrix and then copy, it's the same thing as copying first and then multiplying by matrices. So we were trying to see if we could do something with these axioms, if they were enough to play around with linear algebra. And the first main theorem is that if we were able to prove back here, we were able to show back here that every matrix could be written as a diagram. But with these new axioms, you can actually show that every diagram is a matrix. So you have this bijection between diagrams and matrices of natural numbers. And now you're able to do algebra of matrices diagrammatically, right? So these are the last axioms that you need to do matrix algebra. And they're really nice because they're dual, they're very symmetric, and they encode exactly the most important property of linear algebra, which is linearity. But you actually do need this other axiom here with doing the same thing for the copy. Okay, and the proof here I'm not going to show you, but it's essentially trying to do matrix multiplication graphically. So the proof is algorithmically. You have to think about matrix multiplication, how that would work graphically. But the thing is, our main contribution is not these axioms, but we start thinking more about it, that linear algebra needs more than just matrices, right? Of course, we can't just deal with the algebra of matrices. That's not linear algebra. Linear algebra deals with equations, deal with linear relations in general. Okay, so subspaces, planes, lines, the whole shebang, right? And so we need more than linear functions, which are matrices. We need linear relations in general. So for example, if you have a system AX equals 0, how could you represent that graphically? And the idea is that we have an input and output, that the X is coming in here, it's multiplying by this matrices A. And once it gets to the output, we want it to constrain to be 0. Okay, we want the output of this, whatever is in this wire, to be 0. So one of the ideas that the authors in the past said is to actually, you need to invert the 0 generator. Now the 0 generator is not going from left to right, but it's going from right to left. So this equation here actually is encoding the same thing as this equation. So you have some input, goes through A, and here it's saying that it needs to be 0. So this is how we're gonna represent graphically. So we need to get rid of the idea of functions, which are processes going from left to right. And we can't think about input and output anymore. And things can be going from the left, from the right. So you lose the idea of functions and you start getting into the idea of relations. Also, for example, if you have a system AX equals BY, you need to connect the two matrices in the middle, and then one has to be going one way, one has to be going the other. So the idea is to generalize to relations. So to generalize to relations, you need new generators. But the idea is you're going to have the same exact generators, but they're all flipped around. So you can copy stuff from left to right, but you can also copy stuff from right to left. You can discard from right to left. You can sum from right to left. So you have this instead of these 4 generators, you got the 8 generators to start dealing with relations. Okay, and the nice thing about it is that we can the axioms that we had before for copying and adding, we're gonna have the exact same axioms, but they're reversed, right? To start dealing with relations. And we reverse them and we establish these are going to be axioms of our language. Okay. And the question is about the axioms that I showed you before. For functions, they were really nice. They encoded linearity, and we were able to prove the main theorem that graphical linear algebra could deal with matrices. We kind of want to do the same thing here. What axioms do we need to start dealing with linear relations? Right, so that's the main contribution of our work. We came up with a set of axioms, which turned out to be you need to start using for relations. You need to get rid of the idea of equality, and you need to start using axioms of inequality, which would represent that this linear relation is a subset of this linear relation. Okay. And so you generalize the idea of relations with this new symbol in the language. So we were able to come up with axioms for copy, okay, and we were able to come up with axioms for sum. I won't get into the details of them now. It's just important that the axioms of copy for relations and the axioms of sum for relations are exactly the same, but they just switch the inequality signs. Sorry, so you just literally have these 3 axioms here and these 3 axioms here, and with these new set of axioms, we were able to prove that the diagrams with these new generators and new set of axioms, they're essentially equivalent to linear relations. Okay. So every linear relation can be written as this diagram, and every diagram can also be represented as a linear relation that we used to talk about in the classical linear algebra books. Okay, and this is the main result that we were able to do in this paper. The proof, actually, that's in the paper. I'm not going to go through this, but the proof is essentially with our new axioms, we were able to prove that they're equivalent to the old axioms established by Bocci, Sabanaski, and Zanazzi, and independently by Erbeli and Baz, which they are the ones that developed graphical linear algebra. The axioms they had were not very dual. They had some duality, but they didn't have a lot of symmetry. And we were able to prove that our axioms are equivalent to their axioms in the paper. And the main advantage I'm going to want to show here to you is that because of this these dualities that we get in this new language, anytime you prove a theorem, for example, this is a theorem in the graphical language. For example, this says that relation is total. Okay, this is the various characterizations of a relation being total. Because of the symmetries and dualities of our axioms, we're able to, once you prove this theorem here, you get all the other ones for free. Okay, so you're able to expand on the idea that we had before with matrices, that was buy one get one for free. Now we're able to get 3 for free because of the ways we're dealing with the inequalities. Okay. There are a bunch of other advantages that I didn't mention here because of the time, but read the paper, please, to see. One of their future works is to think about how algorithms work in graphical linear algebra. For example, Gaussian elimination, how you solve a linear system. We're thinking about how to write this nicely graphically. So this is important to be able to explain to people linear algebra through graphically. And one of the other things we want to work on that we haven't established yet is how to deal with orthogonality, how to deal with eigenvectors, SVD, all the stuff that's later on in the linear algebra course. And hopefully one day we can do a undergraduate graphical linear algebra textbook where all the proofs are visual, and maybe we can do that. I want to thank everyone. You can check out more stuff about graphical linear algebra in Pavel's blog. You can contact me, and in January we're going to have a 2-week online course at UFRJ on graphical linear algebra. If you send me an email, I'll send you the link. Okay, thank you very much for listening.
So thank you, João, for your talk. It was very intuitive, very clear. Thank you. So let me see the questions. So we have one question here from Tiago Massoni, and he's asking if are there any empirical studies on the effect of these graphical representations on linear algebra students. Sorry.
No, Thiago, that's a great question. I just been doing it I've been using it in my class, and Pavel's been using it in his class, and a couple other people that we know, but there's no actual true scientific studies on how this affects. That's one thing we want to try out, but we think we need to actually develop the language a bit more to truly use it in a classroom scenario. It's interesting your question, because this work was actually this graphical work was actually started in quantum mechanics using the same kind of diagrams that we had here by a group in Oxford, and they already have a undergraduate quantum mechanics graphical textbook, and they already trying out and actually teaching quantum mechanics to high school students and seeing how that helps. So they're doing the first studies about that. So hopefully we can do that in linear algebra as well. Thanks for the question, Chad.
Okay, any more questions? So if you have other questions, just type. While you were presenting, I have also a similar question to Tiago. I was thinking about visualization. So you are currently, do you have any tool to support, or this is like
Yeah, the same group at Oxford is doing, it has already programmed something that you build the diagrams in Python, and it changes into classical linear algebra code. So they're doing that has a tool to support it. But so the idea is truly you build the matrix by hand, and then since the connection between the syntax and the semantics is very formal, the program already knows how to change it to matrices, and you can use it in MATLAB, Python, whatever. So there's a tool for that. But it's very early stages what they're doing. And there's another group also in Sweden that's doing the same thing. Diagrams become programs, and they're exactly the same diagrams that we have here. That's a nice question. I don't know if I answer exactly what you meant, but.
Yeah, I was just wondering because I think the notation is very intuitive. I was just wondering about the trouble, like to write down this in a paper, and
it's a tool. A tool in the, yeah, we actually use the tool there's a LaTeX tool for writing these diagrams in the last, like, it was built the last year, but it's still very, very tough to do that.
Right. So I see in your paper that you have typed all the rules there. So I was wondering if you have some like LaTeX or something to help.
Yeah, the same group at Oxford, they did the support too for LaTeX as well. So the quantum mechanics group is working more on these practical parts. So it's not before 2 years ago, it was absolutely hell to draw these diagrams. It's better now, but I had a lot of help from people. So.
All right. So if you don't have this reference on your paper, so I'd ask if you could please provide some reference for the LaTeX.
Yes.
Because I think the not person.
Yeah. I'll definitely add
so
that.
I think I have a question here. Last question. We still have 3 minutes. The question is from Rodrigo. It's in Slack.
Oh, okay, nice.
What's the relation with typed linear algebra by Macedo and Nuno from in Portugal? I'm asking.
Oh, sorry.
Because you use the typed language, it would be easy to mechanize it on a proof assistant.
Yeah, Macedo and Oliveira's work was a huge inspiration for us. They're really connected, these two works. We actually I've been talking to Hugo, José, and their whole group in the last month, because we realized it's a lot of connections. But the idea is they essentially did the same thing in the graphical, but they did that in the 1D syntax. So they understood also that copy and sum are the essential parts of linear algebra and how they interact with themselves. So Macedo and José Oliveira already understood that. But they did their work on the 1D syntax, so it's essentially the same idea, and you can prove in their work you can prove a lot of things about block linear algebra, and that's the stuff that we did in the ending of our paper. So it was a huge inspiration for us.
So there is a last question here from Ana Maria Martins. She says, it would be nice to have the diagram from the linear algebra equations, wouldn't it?
I don't know. What do you mean, Ana Maria, by this question?
I don't know. Can I talk?
Yes.
Yeah.
So no, just because if we could have the diagrams generated from they have a problem in linear algebra. They could write it and generate the diagrams and then work with the diagrams and go back.
That's actually equations to the diagrammatic language. Easy, but like I'm actually was looking for students to work on this tool. This is the easy direction. The hard direction is translating it back from the diagrams back to code, to linear, classical linear linear algebra equations, but that's really nice, and that's that group in Oxford I was talking about. That part is already working there too. So but of course, there's a lot of limitations because you have to type it as of a parallel composition. It's easy. It's exactly matrix multiplication. But one of the other operation, the parallel operation, is that students are not they're not too, so like they're not used to building that up. But like but it's a great idea. I'm really interested in that, and that's the reason I wanted to showcase a little bit of graph.
Okay, so we need to finish now. Thank you, João, again for your talk.
Thank you so
Also,
much.
thank you for all the participants in this technical session. Thank you, Gustavo and Volker, for inviting me to share this section. It was a pleasure to share a section for SBMF. And if you have any other questions and comments, please type on the Slack channel. And so come back in the afternoon for technical session 2. Thank you.
Thank you, Patricia.